through is Gauss's law. That's where we left off last time. And I think everybody here has had Gauss's law, haven't they? All right, well, here's the beauty of Gauss's law in a nutshell. Before, whenever we wanted to find the electric field, we had to take a differential chunk of charge on the surface that was creating the electric field, find the vector components of the electric field, and then do an integral of that charge. Really, with the differential electric field, you had to integrate the charge density over where it existed to get the total electric field. And the thing was, there was a lot of vector integrations going on. Here with Gauss's law, the real beauty is, you can eliminate a lot of this. And I'm going to show you through the standard canonical forms, the standard most commonly encountered forms, how come Gauss's law is so powerful. So with Gauss's law, what it actually says is this. You might need to put this thing back upright. Dr. Gross doesn't like it that way. Gauss's law says that the integral of d dot ds over any closed surface is equal to the charge enclosed by the surface. Now that's called the integral form of Gauss's law. The differential form of Gauss's law is divergence of d is equal to rho v, the volume charge density. This is differential, it makes sense, right? Have you all seen a divergence before, the divergence operator? How many have? A lot of you haven't. Do you have your books with you? If you look at the very back of the book, the cover, open it up. The very back of it, keep going. Right there, the very first operator is called divergence. It operates, and it's given in Cartesian, in cylindrical, and spherical coordinates. We're going to cover spherical today, but I want you to make sure you understand. We can actually show how that's gotten about. Simply put, let me just mention this one. This comes a little later. The divergence operator, you don't have to write this down. Divergence of this, you think about this as a derivative operator in the relative coordinate system. Now the result is a scalar, so it's the derivative of dx with respect to x plus the derivative of the y component of d with respect to y plus the derivative of the z component of z with respect to z. That's all the divergence operator is in Cartesian. In cylindrical, will be 1 over rho d rho of rho times d rho plus, and then it'll be 1 over rho times d rho of d phi d rho plus d dz of dz. Do you all see that one? And I'll get to spherical once I go ahead and I have to define spherical coordinates, but the spherical one has to do with, there's a 1 over r squared, and it's d dr of r here, r squared times dr. Then there's plus 1 over r sine theta times d d theta, or d d phi. And I'll get to this operation afterwards because until I'm going to actually be doing problems, it doesn't make sense to go through it. Anyway, there's 2 other terms for that one. So here's how Gauss's law is used. Here's what it means to us. First, if I said I had a charge 5 coulombs and I had another charge 6 coulombs, right here, and I put a surface around there that totally encloses that. And I look and I say, well, therefore, what is the integral of the d field on that surface dot ds, and this is the symbol for a closed surface integral. When you put a little circle, mini circle in the center of that, it means the integration goes over the entire surface. Well, you just have to take one look. It's 5 and 6 coulombs there. It's 11 coulombs inside. That's all it is. Now that doesn't do anything for us in terms of what we can actually calculate. So last time I said if you have just a single point charge, Q, right? And I go out a distance, and I'm going to hold this distance constant. I'm going to use the symbol R for radial distance. I wish I could see the markers. Better markers. I go out a distance r away, and then I put a surface. Here's the thing about Gauss's law you have to appreciate. I'm going to assume I'm at a constant distance. Now you have to have some insight into the way the electric field and therefore the D field is going to sort of map or organize itself. You all agree that if this is a positive charge, that the electric field be radially away from it. Do you all agree with that? And because the D field is equal to epsilon naught in free space times the E field, if it's radially away, the D field will be radially away also. Do you all agree with that? And its amplitude will not be a function of where on the surface that you are. The amplitude will always be the same. Do you all agree with that? So now I can say, if I want to know what the D field is on that surface, I can say that the integral of D dot ds over that surface is the charge enclosed, which is Q. Last time I asked you, well, if the D field is radially outward, the differential surface, and I'll get to spherical coordinates in a second, the differential surface here is equal to r squared times the sine of theta, I'll get to that, d theta, d phi. That's what the differential surface is on this surface. There is no dr. Well, anyway, if I put that in here, really, let me go back a second. You all realize that the D field is radially away, right? A differential surface vector like that would be in the AR direction, would be radially outward. And if I take, and the D field's radially outward, so this dot product will be 1, and then I would get this, I would get D of R, and that's at a given radial distance, times the integral of r squared times sine theta times d theta d phi. And we go from 0 to pi with theta, and d phi would go from 0 to 2 pi. Now I know you haven't had spherical coordinates yet, but just understand the only thing that's doing is giving you the surface area of a sphere. And that would be equal to the charge enclosed. Well, that would be d of r. What's the surface area of a sphere? We did that last time.
4 pi r squared.
Remember that, 4 pi r squared. You need to know that one. 4 pi r squared. And that's equal to the charge enclosed. I'm just going to call it Q. And therefore, d of r right here would be equal to Q over 4 pi r squared in the AR direction. Now, if that's the D field, it's in the AR direction, and I can get rid of this, just put a vector sign, then the E field is what? Look at the relationship. I just take the D field and divide by epsilon, right? Divide this by epsilon naught, and sure enough, that is the E field on the surface. Now we proved that for a point charge, or actually I stated it explicitly. Do you recall that? But this is from Gauss's law, how you could actually determine it. That's one. The next is for a long rod, or remember when we had this problem, we had an infinite line charge. So we're going to put it on the z-axis, and this has a charge density rho L. It's on the z-axis. Now, so assume it's infinite. Now here you obviously see cylindrical symmetry can be exploited. It's cylindrically symmetric. Do you all agree with that? So if I come out a distance, and I'll call the distance rho, and that's a constant, and I make a simple, what I'm going to do is this, I'll lay a coordinate system here. If I take this and make a can out of it, like so, and I do this, and I try to make a can out of it, and the can is going to have a height h, and whenever you're making these surfaces, this is going to, think of it just a can of soup, the outside, the part of a can and the top and the bottom. Whenever you're given something where you have to build, this is called a Gaussian surface. Whenever this was a Gaussian surface, it means a surface, a fictitious surface used to calculate the D field. And it's always going to exploit symmetry. You don't use Gauss's law unless it's a symmetric problem, where the D field will have the same magnitude, just by your insight into the problem. Whenever you make these surfaces, always make h equal to 1 meter. Don't leave it as an arbitrary height, because what happens is people forget to divide it out or something like that. Just make it 1, you can't mess it up. Now, I'm out a distance rho, and I need the differential surface on this can surface, right here. Well, this differential surface on the outer part of the can, where the label would be equal to rho d phi, and then it would be dz, and it would be in the a rho direction. Do y'all remember that? Think about this, the wiper arm right here, right? That would be rho d phi, correct? And the height would be dz. Do you all agree with me? But the surface always has a vector sense, and I think I talked about the floor, and if I talk about a differential surface in the floor, if it was x and y, it would be dx dy, but the vector sense would be az. Do you remember this? It always points out. So this would be the differential surface here. But what about the top of the can? There's also like a differential surface here, right? What would that be? Well, what about in the radial direction? It would be what? D rho, right? It would be this ds on the top of the can would be d rho, right? But then there's this, the angular part right there. It would be rho d phi. Do you all see this, class? Can you see it? So this is going to be rho d phi, and what would be the vector sense on the top? I'll give you a tip. It can never be any of these coordinates in here. It can't be rho, can't be phi, so it has to be az. Is it up or down? Up, az, positive az. Right. And then on the bottom here, this differential surface would be right on the bottom part of the can right there. That would be simply, ds would be same exact structure as that, d rho times rho d phi, but it would be minus az. You agree with that? Now, when you go about this, because the d field itself, and you have to have insight to this, you all see from this that the d field will be radially away. It's only going to be an a rho component, isn't it, class? So when I take a look at the integral right here, the integral of d dot ds over the closed surface, I can say it's going to be the integral on the outer part, which is going to be the integral of d rho. Actually, it's going to be a rho component of d in rho direction, and then it's going to be times d. It's dot product of ds. A rho dot a rho is 1, so I'm not going to put the a rho there, and I get rho d phi dz, and phi goes from where to where, class? Remember, phi is the measurement between x-axis and the radial vector rho, right? It's right there. Where does it go from?
0 to 2 pi.
2 pi, yeah. So it goes from 0 to 2 pi, and z goes from where to where? 0 to 1. So that's the first one. Now the other part I'm going to show you. With the top part of the integration here, it would be d field, and I'm going to put now vector, or I'm going to actually put d rho of rho, a rho here, so I can make my point. That's the only component of the d field that's going to exist. Do you agree with that? There is no z component. I put that there, and I have to have a dot product of that with ds. Well, ds is equal to rho d phi d rho. This is the top surface. And phi goes from 0 to 2 pi, and rho goes from 0 to rho. And that causes a bit of a dilemma, because you can't have the symbol inside this integration operation equal the boundary point. So what we do is usually put a prime there. And it doesn't really matter about that. Now this is in the a rho, or I'm sorry, this is in the az direction, right? Now here's my point. You don't have to evaluate this integral. Here's why. What is az dot a rho? Do you remember dot product? It's 0, isn't it? As a matter of fact, let's make sure everybody appreciates this. If I have ax dot ax, that's 1. Do you, everybody agree with me? What is ax dot ay? 0, right? What is ax dot az? 0. All right, now that's Cartesian. A rho dot a rho is 1. A rho dot az is
0.
A rho dot a phi is 0. Only a vector, if it's an orthogonal system, a dot product of a unit vector only in the same direction is 1. Any other direction, any two that are orthogonal, the dot product is 0, because it's the cosine of the angle between those two vectors that you're really taking. Which means this one goes to 0, and you all see the bottom one would also go to 0 without even writing it down, because it's the surfaces in the minus z direction, az direction. Y'all see that? So you don't even bother doing that integral. This is the integration you're going to do. Now this integration is really d rho, but it's holding rho constant, right? Do you agree with this? So when I have here, I've already got rid of a rho dot a rho. I knew it was 1. When I integrate dz from 0 to 1, I simply get 1. And then I integrate that d rho as a constant, so now I can take d rho here, just leave it there, it doesn't have to be a function of rho, times rho, because it's not, the integration isn't with respect to rho, and now I integrate from 0 to 2 pi d phi, and that gives me simply 2 pi rho d rho here is equal to the charge enclosed, which is simply, how much charge is here? If rho L is what? Charge per meter, right? If I'm 1 meter long, how much charge is there? Just rho L, right? Times 1, agree? So it's just rho L. So you can put rho L over here, and that means d rho as a function of rho is simply equal to the charge, line charge density, if it's constant, over 2 pi rho. And if you wanted to make it a vector, you would put a vector here and you would put this direction, a rho here. Now, how do I get the electric field? Right. And if I divide this by epsilon naught, now I have the E field as a function of radial distance. Do y'all remember when we proved that? When we did the vector integration? It's a lot easier doing it this way. It becomes almost trivial in most cases, if there are highly symmetric problems, all right? Now, I'll tell you how this also works. The next thing they go to, these are like incrementally increased, or they're incrementally difficult, more difficult problems. Now instead of just a line charge, I'm going to have a pipe of a certain thickness, certain radial thickness, and it'll be a constant charge density. And now I want the D field there. Well, inside the pipe, where there's the constant charge density, the D field is going to be different, and it'll have a much different form than outside the radial distance where the pipe is. And we'll do that problem in a second, but let me get into spherical coordinates now, okay? How many have had spherical coordinates? Didn't you all have them in physics or not? You should have all been exposed to them in physics. I'm not sure about your math department, but even there, they should have shown you spherical coordinates for when you did integrations, volume integrations in calculus, or bodies of revolution type things. All right, I'm going to go through them again. And one thing about being in the engineering curriculum, usually you're exposed to important concepts many times. You get it in physics and math, and you get it in a couple of courses here, and they keep on reinforcing how the concept, whatever it is being utilized, how it's used. And spherical coordinates, first, are very important for defining regions of space, and they're also what they have the ability to do is simplify a lot of the mathematics and make the problem easier to organize and discuss. And where we use a spherical coordinate system or a cylindrical coordinate system is when the symmetry of the region dictates it would be applied, it should be applied. Okay. Now, here, we're going to be talking about spherical coordinates, so let me do it this way. So, usually Dr. Wentworth's book starts with Cartesian coordinate grid, and then he lays the spherical coordinates or cylindrical coordinate grid on it. So, here's what happens. If we just take a vector, say we take a point here, a point X, Y, Z in space. Well, if you go from the center, from the origin, and draw a vector out to that point, that is called, the distance from here to here is called R, and it's the radial distance. He always uses a small r. It's just the radial distance. So, in terms of X, Y, and Z, R is what? simply the square root of x squared plus y squared plus z squared, correct? That would be the rate relationship. Then, what he does is this. If you take the projection of r into the xy plane, that would be like the radial distance rho. You follow me? And here, what am I really doing? Well, if I want the projection of this vector into this plane, what would it be? If this, oh, I didn't say this too. Let me make one statement. You know, this angle from the z-axis to the rho vector is considered phi, correct, class? That phi still applies for spherical coordinates. Those two are the same. There's one that is slightly different. The measurement from the z-axis to the actual r vector, the angular difference right here, this is called theta in our book. The symbol is theta. So generally speaking, we'll get to this, but that's theta. And let me go ahead and do some definitions. Can you all see what I'm talking about there? Now, if I want the projection of this vector into this coordinate system, what I can do is say rho would be equal to simply r times the sine of theta. Y'all agree with that? Because really that rho distance is this distance, isn't it? Y'all agree with that? So that would be rho. Now, watch this. But if I wanted to know what the value of the x distance would be, say if I had that, then if I take r times the sine theta, I get rho, and then if I multiply rho by the cosine of phi, I would get x. So one thing I can do is put down x would be equal to r sine of theta, and then it would be times cosine of phi. Can anybody see what y would be? This would be y distance.
R sine theta sine phi.
Exactly. Now it's going to be r sine theta takes you down, gives you rho, right? Multiplying by sine phi, right? The sine of phi would give me this distance, correct? So that would be r sine theta sine phi. He'll have this in his book. All right. Another thing I'm going to show you is how would I get the z height of this from r? That's this height. Wouldn't it be what? R times
Cosine theta.
R cosine theta, right. So you could get z would be equal to r times the cosine of theta. Now these are transforms. If you're in spherical and you wanted to go to Cartesian, you would do this. And if you are in Cartesian and you want spherical, I started out, I'd say that would be r, right? Now, and that would be rho if you wanted cylindrical, but what would phi be? Well, phi was what? Think about this for a second. If this is x and this is y, right? And this is my point xy, then phi is measured from the x-axis, right? So if this is my point x comma y here, then I could say what? First I could say that the tangent of phi would be equal to y over x, right? Or phi would be equal to tan minus 1 of y over x. Y'all see that, class? Really, I'm just saying if this distance is x and this height is y, well, opposite over adjacent is tangent, right? So if I wanted the angle, I would take the inverse tan of y over x, and that would give it to me. Do you follow me? So that would give me this one. It would be tan minus 1 of y over x. And how do I get theta? There's a lot of ways to get theta. Well, what could I do? I've got r, right? There's a lot of ways to do this. I have r, don't I? X squared plus y squared plus z squared square root. Well, I know that what? R, or z over r would be what? The adjacent over the hypotenuse is cosine, right? So I could say, therefore, cosine of theta is equal to, and that would be z over the square root of x squared plus y squared plus z squared, which means theta could be gotten from cosine minus 1 of z over square root of x squared plus y squared plus z squared. And that's just one way. Can you think of another way we get it? Well, look, we have height z and we have rho, don't we? Right, well, wouldn't it be opposite, or rho over z would be equal to tangent of that angle, right? So I'm going to tell you there's many, many ways of getting this. The idea is just make sure you understand where the angles are with respect to, all right? And then from there, if you're in Cartesian, you can get the spherical coordinates. That would be that, and that, and that, right? If you're in Cartesian, you want the cylindrical, you can get rho and phi, and z is the same, correct? And by the way, if you're in spherical and you wanted Cartesian, you could get them this way. So you can go any which way you want. That's the relationship. Now, the next thing I want to do is talk about the differential vector, or the unit vectors in the associated direction. This one's a little tougher to see. Let me sketch a new thing over here. In your book, who has a book? You got a book. Let me see if I can show you where this is in the book. The sketch is here kind of important. Spherical coordinates back this way. Do you see where spherical coordinates are in EL? It's on page 128 in the bottom. Or 128 is the drawing. I want to show you the unit vectors because these are the more difficult ones. So I'm going to try to sketch this thing well. That's x, that's y, and that's z. Now if I come out a distance rho away, here's what you have to understand. A rho is a unit vector always in the radial direction. It's always pointing radially away. But what that means is, and this is important, remember that's theta, right? And if I projected the point down here, and that would be rho, then this would be phi. Keep that in mind. Now, a rho always is radially away, but notice this one thing. In terms of its vector point, its absolute pointing direction, if we change theta, you see how a rho now changes its actual orientation? So remember that. Only in Cartesian coordinates do the unit vectors remain in the same exact direction always. AX, AY, AZ never change their relative direction of pointing. Here, the real pointing direction is also dependent on A theta and A phi. All right, so it's not an absolute. It's useful in this coordinate system we're talking about, but that's a rho. Now, A phi is the, well, let me do A theta next. A theta points this way. A theta would be like if you took this and you wobbled it, hold phi constant and wobble it in terms of a differential d theta. Do you see how this tip would move in this arc ring that way? You don't see it? I wish I had a longer, there's no pointer in this classroom. But if I just use my arm here, and you look at the tip of my fingers, this is going to be holding the fulcrum, like right here. And if I move this tip, you see how this arc length is moving? That is in the A theta direction. And you'll notice it's pointing from the North Pole towards the South Pole, you might say. It's pointing this way, not this way. It's not aiming at the North Pole. Do you all see that? It's important to see that. That's A theta. Now, A phi, and this is one you have to understand, A phi is actually at the tip of this axis, it's pointing this way, right? It's at the wiper arm. If you take that rho vector, right, and you look and you wobble it, put a d phi change, you can see the tip is moving in a partial arc, short arc, and it's pointing, the direction is pointing, where I have it here would be, and it's hard for me to draw these, by the way, that would be A phi. Can you all see that? Now something to keep in mind, remember this is a right-hand coordinate system. So with unit vectors, if you take one and cross it in the other, it'll give you the next one, if you do it right. So if you take A rho crossed into A theta, you get A phi, and I better put this up here. A rho crossed into A theta, you get A phi. Now can you see that? Just take your right hand, use your index finger on your right hand, and aim it in the direction of A rho. And then take it and use it as a wiper arm, and then over the smallest angle, wipe it into A theta. You see how your finger's pointing right into the board, your thumb, I mean? You all see that? So into the board would be A phi. If we were over here and we did it, then A phi would be pointing out of the board on this side. Just think about it. Come out here, A rho's that way, right? A theta is down this way, A phi would be coming out of the board. What I mean is A phi can point in or out of any direction depending on the relationship of the angle phi, right? I think you can visualize this in your mind, right? All right, now, what about, do the next one. When I take, that's rho theta, what if I have A theta crossed into A phi? This one's probably a little hard to see. Well, I have A theta pointing down, right? Crossed into A phi into the board, right? Gives me what? My thumb is A rho pointing out. Do you see it? So I have A phi, A theta crossed A phi is A rho. And then you could say, what's A rho? Actually, I should do it this way. Let me do A phi cross A rho. What is that? Just think of that point. That's pointing in, right? A phi is in, right? Crossed into A rho, A theta, right? Does that book show the unit vectors very well? He shows you a ds vector surface, but the problem is I don't believe he shows you the unit vectors associated with spherical coordinates. Now I have some overheads that I'm going to I'll put them on OneNote that really do a better, give you a better visual tool to try to actually understand the unit vector sense. It's really important to do it. While we're on this topic, we did the differential surfaces for Cartesian, a differential surface and volume for Cartesian, didn't we? And we did it for cylindrical, correct? And we haven't done it for spherical, and we're about to. Spherical is a little tougher for me to draw, and I'm going to do it right there. Try to appreciate all these differential surfaces have to do with differential distances. In our case, differential distance d rho, differential distance rho times d phi, and a differential distance which should be equal to another one, r d theta, and that's going to be in the theta direction. So I'll try to construct this. So please realize I'm not real good at this. So this is, well, I haven't been in the past. This is my differential there. Then this sweeps this way, and this sweeps this way. Now follow me, I'm trying to build a cube here. So the differential distance radially would just be d rho. Can you all appreciate that? Now the differential distance this way, this, which is going with d phi, would be equal to r d theta. And that should make sense. That's a wiper arm. The wiper arm's length is r. It's moving d theta, right? Here's the one that gets people. This distance right here, you have to project down here almost and see it's really going to be, this is really rho d phi right there. But what is rho? That's equal to what?
R sine theta.
R sine theta times d phi. And that's what that distance is. So that differential surfaces, or the differential volume, dv, or d vol, is equal to the differentials, which is going to be equal to r sine theta times d phi. Then it's equal to r d theta, and then it's equal to d, this is dr right here. That should be dr. That's the differential unit of volume. And what they usually do is take the r's and multiply them, so we get differential unit of volume, or just dV being equal to r squared times the sine of theta. And then it's usually given as d phi d theta dr, and that's differential unit of volume in spherical coordinates. Most of you remember something about that, right? All right. It's just r squared sine theta d phi d theta dr. And the order that these are in makes no difference. You could put dr first if you prefer, d theta d phi, or whatever. And here, he actually shows you what the differential surface looks, or the differential cube looks like at the bottom of page 128. And he shows you the differential volume. Now, I just want to mention a couple things about the differential surfaces. If you look at this outer surface here, this is right here on the outer part. What vector sense would be? That ds would be in what direction, right here?
AR.
Yeah, it's AR direction, but what is it actually, the differentials? What is the differential this way? R d theta, right? And the differential this way? Can you say it?
R sine theta.
D phi, right? R sine, R times sine theta d phi. Which means it's R squared sine theta d phi. Agreed? And what direction is it in? AR. That's that surface. Can you all see that, class? Take a good look, make sure you're convinced. And now he shows in your book, what's this bottom surface's differential right here?
R sine theta.
Well, what direction first?
Theta.
A theta, right? It's going to be A theta. And then the differentials. This one is
R sine theta.
d theta, right? R sine theta d phi. And then this one, or I'm sorry, this one.
dr.
Dr. Y'all see that, class? Okay. Now what about this differential surface right here on this edge? First, what vector sense? Careful on this one.
Minus A.
Very good. It's A phi for sure, but it's minus because it's pointing this way. If you can appreciate it, it's pointing like this, right? Coming out of the board. The way I have that, it would be A phi would have a sense. Positive would be going, if you're looking down the z-axis, counterclockwise. So this would be minus A phi, and go ahead with the differentials. This way?
DR.
dr, right? And this way?
D theta.
R, right? D theta, right? Agree with me, everyone? And you have to kind of mess with these things for a while to get them, but just so you understand both the magnitude and the direction of them. Okay, class? Now, the reason I did that is because the next problem we're going to do, or the next thing we're going to do, is apply Gauss's law to something with spherical symmetry. We already did the point charge, right? But now we're going to have a spherical volume with a charge density. I didn't check the weather this morning. Is it good, bad, or terrible?
It's gonna get bad around 34.
So no rain later?
That's when it's gonna start raining.
Oh, it is going to start raining.
It jumps up to like 75% around 3.
Thunderstorms?
Mm-hmm.
Ooh. Not good. For what I have planned. What's that?
Such 40 right now on my phone.
It depends if you use AccuWeather or NOAA or weather.com, and I get different things. If I look on AccuWeather, I found it's usually the best if you go to AccuWeather, and but they all based on the same observations from the National Weather Service. I mean, they have the same radar map. There's no difference there. How they actually interpret what's going to happen is a little different. So now here's the problem that's set before us. I'm gonna have, this is a good one, let's see who gets it. I'm gonna have a sphere, and the sphere has a radius of A. And just draw a line around it. It's centered at the origin. Now inside this distance A, when R is greater than 0 and less than or equal to A, I'm gonna have a charge density, rho V, it's a volume charge density, equal to just some value. I'm gonna use, say, K, capital K. And then I'm gonna say rho V equals 0 for R greater than A. So try to understand this. It's like I've got a styrofoam ball with a certain volume charge density that's not a function of position. And I wanna know the electric field everywhere, inside and outside of that styrofoam ball. Does that make sense to everybody? Please make sure you get this one. This is critical because this will show you how to use Gauss's law to solve it. Now, to do this problem using the differential form of the electric field where we take dq and then get dE and then integrate that is a pain. Just level them. But using Gauss's law, it's trivial. And here's how. With Gauss's law, we first say for R less than A, less than or equal to A, greater than 0, we can make the claim the integral of d dot ds is the charge enclosed. Just write that. So now what we have to do is two things. We construct a Gaussian surface that defines my little statement. So I come out some distance r, and then I draw a spherical shell around there. I didn't say this, but does everybody agree that the electric field is, that this is a spherically symmetric problem? Do we agree with that? And by that fact, I'm going to make this claim that the electric field is going to be radially away at every point. Do you agree with that? And that means the D field is radially away. And furthermore, I can make the claim that the D field will only be a function of the radial distance away. And here's how I can do that. I didn't say this earlier, but if you stand and look at that sphere, and I'm at a given distance away, call it D, and I move at any angle theta or phi, but holding the distance constant, it looks identical, doesn't it? And there's a math argument on this, a mathematical argument that says if that be the case, then the actual fields involved that we define can only be in directions that are radially away from that, because this is spherically symmetric. Now, I'm not going to try to do any proofs, but I'm just saying that there is a proof for this somewhere. So I can say this, the integral of d dot ds, well, this is really going to be a double integral, and it would be the D field only is going to be in the R direction, AR. Now the differential surface, now on my differential surface right here, I need my ds, right? Remember, R is held constant, so it's going to be in the AR direction, right? I know it's going to be AR. And the differential surface we just did, that's going to be R squared times the sine theta, d phi. I don't know if you remember that, but we just did this one. It's R d theta in the a theta variation, and then it's going to be R sine theta d phi in the phi direction, which multiply them together, you get R squared sine theta d phi. The limits on this, for theta, where does theta go from, by the way? I didn't mention this. Remember, this is theta, where does it go from, if this is collapsed from 0 to, say,
Pi.
exactly, from 0 to pi. Where does phi go from? Phi?
0 to 2 pi.
0 to 2 pi, remember that. Phi is the one in the xy plane. It goes all the way around, 0 to 2 pi, 360 degrees. Theta only goes from the North Pole to the South Pole, or 180 degrees or pi radians. Now that's equal to the charge enclosed. So how much charge is enclosed? Well, that would be the charge density, K, right? That's a constant. By the way, charge density can be a function of R. It does not have to be constant. And if it was a function of R, then these integrations change. And I'm going to tell you, people memorize formulas about volume charge density. they always assume it's constant, and then that assumption breaks down because I usually give volume charge densities that are function of radial distance, not constants, usually. So remember that. So now this is happened to be a constant, but then it's time the differential volume, right? Charge density times differential volume integrated over the volume. What would the differential volume be? You remember? It's the same as this, only with one multiplier, dr, isn't it? It's going to be r squared times the sine of theta, right here. Then it's going to be d theta, d phi, dr. Put the triple integral here. Theta again goes from 0 to pi. Phi goes from 0 to 2 pi. And where does r go from? This is important. It's going to go to 0, dr, actually, I should use this. It's only going to go from 0 to r, not 0 to a. That's always a typical mistake. It's going, because this is Gaussian surface is between 0 and a, isn't it? I'm saying this outer radial distance right here is a. So now I go from 0 to r here, and really what I should do is put a prime here for my r. All right. I'm going to tell you this, I'll do this one time here. When we do these integrations on that side, let me clue you in. K is a constant, right? If K is a constant, it's just the volume charge density times the volume of the sphere of radius r, right? How many know what the volume of a sphere is? Do you? It's 4/3 pi r cubed, right? 4/3 pi r cubed. I know that, so I know this integration is going to be 4/3 pi r cubed. That I know times k. Over here, I'm going to do these integrals, but I'm just telling you what the answer is. I know that the d field here is in the radial direction, and it's only a function, it's not a function of anything but radius. It's not a function of phi or theta in terms of its magnitude. I know ar dot ar is 1, so I can take dr out in front, and really what that is the integral of the surface area right there, right? ds. Well, I know the integral of a surface, I know what the surface area of the sphere is of radius r. What is it? 4 pi r squared, right? So I know this is going to be simply 4 pi r squared times dr. I know that. And when I would do this problem, this is what I would do. And then to calculate dr inside there, I would just divide that side by 4 pi r squared, and right? I might as well do it right here. I can, from seeing it, I can see dr would be equal to what? 1/3, right? The pi's go away, 4's go away. And then I have r squared into r cubed. It would be 1/3 times r, right? Times k. And that would be for r less than a. Less than or equal to a. But I'm going to do the integral one time, just to show you. So when we do this integration right here, I can take dr out in front. And then I'm going to go ahead and do the integral. So now I have an integral from 0 to 2 pi right here. And I have an integral from 0 to pi, right? The first one, sine theta, right there, d theta. And then I have a d phi integral here. And I have r squared also that can come out in front. Now what I've done is parse this integral into parts that are dependent on theta. So the only part that's dependent on theta is sine theta. So I leave that here. Then I have parts dependent on the phi, which is d phi, and there's nothing else that's a function of phi, correct? From 0 to 2 pi. And the r squared, there's nothing that integrates with respect to r, so I'll pull that out in front. That's how I do these integrations. Now if you look at this, I integrate from 0 to 2 pi d phi, and I get what? Just look at it, class. Just 2 pi, right? So now I have 2 pi r squared dr. Now I integrate sine theta, which is minus cosine theta, right? So now I have minus cosine theta evaluated from 0 to pi. Some of you had me before. Whenever I have a minus sign at the end of an integral evaluation, what do I do with the limits usually, class? I'll swap them and make it plus. So I'll go 0 to pi and make that plus. All right, now just look. What is the cosine of 0? 1 minus the cosine of pi. What's cosine of pi? -1. So it's 1 minus a -1 or 1 plus 1, which is 2. So 2 goes here. Or makes this 4. So that's 4 pi r squared dr. Now on this side when I do it, I'm going to do the same thing except I have the r integration. So I have k coming out in front, right? And then I have an integration of r squared dr, prime it a little, from 0 to r. I also have an integration of d phi from 0 to 2 pi, and I have an integration of sine theta, d theta from 0 to pi. I don't know if you do this, but when I do integrations that have, like, they're functions of 3 different things, the kernel of integration, I try to break up the integral into its respective parts, things that just depend on the angle that I'm going to integrate over, or the differential I'm going to integrate over. So for this one, what happens? Well, that's k, right? Now, when we integrate r squared, r prime squared, dr prime, what do we get?
R cubed over 3.
R cubed over 3. Evaluated at 0 is 0, isn't it? So it's really just going to be r cubed over 3, right? So I can put this times r cubed over 3. Now when I integrate d phi, I get just phi from 0 to 2 pi or 2 pi. And then when I integrate sine theta, I get minus cosine theta. I'm just trying to do the parts for him. Minus cosine theta evaluated at pi would be -1. So minus a -1 and plus 1. And then it's going to be what? It's going to be, this is going to be 2 because it's going to be minus cosine of 0, which is 1. So it's 1 plus 1 is 2. So make a long story short, that's 2. And then you can see I've got 4 pi there, 4 pi there, that cancels. I have r squared, r cubed, makes it r here, right? So it's r, it's basically this answer, r over 3 times k. And that's doing the integration, sorry. I don't mean to bore you by doing that, but at least one time you have to hear somebody talk their way through it and show it to you, just once. Now, so anyway, this is what it is for r less than a, right? What is it for r greater than a? Well, you always write Gauss's law. Do yourself a favor, always write the integral of d dot ds over the closed surface is equal to the charge enclosed, or the integral, yeah, just put the charge enclosed, q enclosed. And I'll make a point here. Now, Dr. Wentworth is very smart doing this thing. This integration, if it's in spherical coordinates, listen, it's always going to be dr. It's going to be the r component of the d field, right? Which is a function of r. If you want to put that in there, you can, you don't have to. It's times the surface area. Well, the surface of a sphere never changes. So it's always going to be 4 pi r squared. Now, this integral will always be that. It never changes if it's spherically symmetric. This may change. It depends if the volume charge density is a function of position. But it's always, nevertheless, it's always the total amount of charge inside the region, if it's spherically symmetric. Well, how much total charge is inside this region? Think about this logically. You're engineers and you're smart. I've got a sphere with a radius of a, right? Now I'm at a distance greater. I'm not inside, I'm outside that sphere, right? Is the total amount of charge ever changing? Now it's a constant, isn't it? And how much is it? Well, it's going to be the volume charge density times the volume. So here, I can do the integration. It would be this integral right here, right? Only it would be evaluated not from 0 to r, but 0 to a, right? And the only thing that would change is instead of r cubed there, it would be a cubed. Follow me? So that means on this side, I have k times a cubed over 3, and then it's going to be times 4 pi. On this side, I have 4 pi r squared. Is everybody together with me here? I've got one important point to make. Now, y'all see that the 4 pi's go away? Can y'all see that? So I'm gonna make it go away. Now, you'll notice the r squared does not cancel anything, because that's a fixed distance, a, right? So now just divide through by r squared. And now I have the D field outside the region. The point I'm also gonna make is you'll see how the D field falls as 1 over r squared. Let's go ahead and get the E field while I'm at it. How would I get the E field outside that region? That's right, just divide by epsilon naught. And then I'd have the E field and just the E field in the radial direction. And one other thing I'm gonna show you. I said this, I think it was last class. You see how it depends on 1 over r squared? Anytime you have a finite amount of charge, as you get a great distance away, the E field always falls off as 1 over r squared if it's a static charge density, if it's not a varying charge value. You follow me on this? And it's very important it does, and in fact it does here. Now if it's an infinite volume of charge, it's different. But if it's finite, it always falls off as 1 over r squared. Got that, everyone? Important point. All right, good. Now, I like to do one more problem with cylindrical, and I'm just going to tell you that with cylindrical coordinate problems and spherical problems, Dr. Whitworth's book has some pretty good examples. And when he talks about Gauss's law, I'll get to voltage in a second, but why don't we take a look at 332, and this is something that does not have a constant charge density. Back up before I forget. All right, for this problem, they have, this is going to be in cylindrical coordinates, so it's the z-axis, and they say they have a wire of a certain thickness. Try to draw it, and I'll tell you a tip. With these kind of problems, it's very important that you get used to sketching something, even if you're not a good drawer. It'll give you a mental image to refer to, or an image to refer to. Now, this has a radius of A, and can you tell me what the limits are in that inner radius? It's going to say a wire and has a charge density of such and such up to a certain point. Just give me rho V, that'll do it.
What page did you say?
6.
Go ahead. 6 row? 6 row?
Yeah, 6 row. C over centimeters cubed.
He likes to do centimeters cubed. I don't like that. So it's a little tricky there. I always put it in meters cubed. Just keep in mind. And I'll get to that in a second. And that's between where and where? For row?
Yeah, 0 and 8 centimeters.
From 0 to 8 centimeters. And it's 0 outside there, right? Rho V equals 0 for rho greater than 8 centimeters, is that right?
No, yeah, rows between 0 and 8, yeah. Less than or equal to 8.
Rho greater than 8 centimeters, it's 0, right? Rho V is 0 outside that region.
Oh, yeah.
What it amounts to is we have a wire and all the charge is inside this wire. So this has rho V. That's the charge density inside the wire. You'll notice it's a function of radial distance. Now, when we do these problems with Gauss's law, you have to partition the region into inside the wire and outside, so you start inside. You don't have to, but I do. So this is going to be for rho greater than 0, less than 8 centimeters. That's my first region. And now I write Gauss's law, which is the integral of d dot ds over this closed surface is equal to the integral of rho v dot dv over the volume. Just write that as in that form, not without any limits. Now I'm going to show you have to do this. I have a different colored marker. I think this blue one works, but I don't. Now you go ahead and define a region inside the region inside rho equal 8 centimeters. So draw a little can if you can. Symmetric with the z-axis. Make that can have a radial distance of rho. And here, make the height of the can 1. Now, this is important. This is the integral of d dot ds. That's vector products of the surface. Do you realize the d field's always in the radial direction, right? Can you all give me that one? It's cylindrically symmetric. The d field has to be in the radial direction. Agreed, class? That means when we do the integral of d dot ds, it's really the d fields in the radial directions times just the surface area associated with the label of the can. Think of that that way, right? That's surface area. So this will always be in cylindrical coordinates, just d rho. We know it's a function of rho, so I'm not going to even put that there, times the surface area of that can. The outer surface, what is the surface area of a can? It's what? The height, right? Times the perimeter, and the perimeter would be 2 pi rho, wouldn't it? The perimeter of that? Or really, when I say perimeter, I mean this. It would be that length times this height. So that's going to be simply 2 pi times rho times h, and I always make h 1. Don't ever make it just h, because somebody's going to forget to divide through by it, and it'll mess things up sometimes. Now I have that, it's equal to the volume charge density. Well here, that's a function now of position, rho. And I'm going to do one thing. 10 to the minus 2 meters is equal to 1 centimeter. That means centimeter cubed is what? 10 to the minus 6 meters cubed, right? Do you agree with that? A centimeter cubed is 10 to the minus 6 meters cubed, right? So what I like doing is, that means it's this, really, and I like to put it in terms of coulombs per meter cubed because I'm used to MKS units. And this can throw you at times. So I just put, it's this times 10 to the minus 6 coulombs per meter cubed. I forget about the centimeters, all right? Y'all follow me what I've done there? Oh, I'm sorry. 10 to the 6, you're absolutely right. And if I was smart, I would have done it like they teach them in chemistry. You would have, if it was 6 rho coulombs per cm cubed, then it would be times, and then you would have 10, oh, wait a second. That would be 10 to the 6 per meter cubed, and that would cancel. So here, you would get a triple integral of rho v, and rho v would be 6 rho times 10 to the 6 coulombs per meter cubed times the differential volume. And what is the differential volume here, class? It's going to be what?
R sine theta.
It's, well, no, this is cylindrical. It's rho times d phi, right? Times d rho times dz, isn't it? Right? Rho d phi is that differential wiper arm. Then d rho is the radial differential, and then the vertical is just dz. Now, we have that, and it's gonna be, I'll just get rid of that, and put this coulombs out here. So where does phi go from? That's the first integration. Go ahead. 2 pi, right? And rho, it's actually gonna go from 0 to rho, right? And so we have to prime that rho. You don't have to do that, but you're supposed to mathematically, because the kernel of integration, the kernel is anything inside here without the differentials. The kernel of integration cannot have variable symbols that have to do with the limits. It's a no-no. Engineers don't care. They just don't. And then for dz, it goes from where to where?
0 to 1.
Yeah, and in Whitmore's book, we'll have 0 to h, but always make h1. If you're ever given the opportunity to choose the simplest value. All right, now when you do that integration, what do you get on this side? Well, I'll take the 6 times 10 to the 6th out in front because I don't care to deal with it. And then I have an integration from 0 to 1 dz, and that's kind of easy. Then I have an integration of d phi, right? And that goes from 0 to 2 pi. And then I have an integration of these, the rho, and that goes from 0 to rho. It's actually rho prime d rho prime. I changed the order of them. So if we do this, this is 6 times 10 to the 6th. From dz from 0 to 1 is just 1. And then d phi from 0 to 2 pi is just 2 pi. And then rho prime d rho prime integrate. Rho squared over 2, right? So here it's going to be rho squared over 2. And that's equal to 2 pi rho times d rho, which means now I can cancel. I've just carried this down here. I can cancel the 2 pi, correct, class?
What happened? Shouldn't it be rho squared, rho prime squared in the integration?
Oh, yes, my bad. You're absolutely right. And I'm glad you caught that. And that means this is rho cubed over 3. My bad. Thank you. I guess I'm not too attentive to detail today. Okay on this one? Thanks for catching. When I go ahead and do this, first thing you notice is the 2 pi cancels, right? Then one of these rows cancels one of those rows. So I have rho squared. And then that's it. So that's d rho, and that's for rho from 0 to 8 centimeters. Now, this can just go away right there. Now, when we go outside for rho greater than 8 centimeters, what happens? Again, state Gauss's law. Closed integral of d dot ds is equal to the integral, or really it's equal to the charge enclosed, Q enclosed. So what happens? Now our region does this. Instead of being limited right here, now what happens is this region does this. Now it's a bigger can. And I'm outside the inner region, right? And this now is my rho. Now, the question I have is, since I'm outside the region, only this region from here to here, the charge inside there I worry about, correct, class? When I do this, the integral of d dot ds is always going to be for cylindrically symmetric systems, just d rho times 2 pi rho. For the charge enclosed, it'll be a triple integral, right? Of rho v dv. But actually, it will be an integration with limits. And now we would take the integration, and I'll put this here, of 6 rho, it's actually, 6 rho times 10 to the 6th. All right, and then it's going to be times rho d phi d rho dz. So let me do something here. I know z goes from 0 to 1. Where would d rho go from on this one? Remember, it's the volume charge. That's from where to where?
0 to Z. Or, no.
0 to 8.
0 to A, the limits, which is 8 centimeters. She's right, right? It's only the region where the charge exists. It's not 0. So it's 0 to 8 centimeters. And we can leave it as A and just call A 8 centimeters if you want. All right? And then when we do phi, phi goes from where to where? Phi?
0 to 2 pi.
2 pi, right. So that means this becomes 6 times 10 to the 6th times 1 when we do dz. And then from 0 to 2 pi, d phi is times 2 pi. And then we integrate from 0 to A right here. And that would be rho squared d rho, which means this whole thing becomes 6 times 10 to the 6th times 2 pi times a cubed over 3 right here. And that equals 2 pi rho d rho. And I think you can see what I'm up to. I'm just about out of time. So now I can see one thing happening right here. When I look at this and this, I'm going to cancel the 2 pi's, all right? Then I'm going to cancel one of those, or I'm sorry, I'm going to divide by rho. I can't cancel any rho. So I have rho down here. And this, we can erase this part. This is the answer for rho greater than 8 centimeters. Does everybody follow me on that? So that's Gauss's law with doing problems. And I'll say one thing too, that the differential form of Gauss's law is simply it's using the derivative operators on the D field to specify. I'm going to give you some problems associated with that, but there's not much I can talk about. I write an equation, I take derivatives. That's the only thing it boils down to. Okay? And we'll pick it up there, and then hopefully next class period we'll talk about voltage and maybe, if we have time, boundary conditions. Okay? You all had this before in physics, though.
This is Cal 1, 2.
For cylindrical and spherical courses.
Yeah.
But you've been exposed before is what I'm really getting at, and so this should be just sharpening things up for you. If you have questions, I'm available now.